Hey guys, Brandon here. Sorry if I had a little lag at the beginning of the video. I hit the camera button and it just kind of went whoosh on me for a second. Today I'm going to be talking to you about physics. I'll be talking about physics in all the podcasts that follows. And one of the big topics I'm going to be talking about is actually waves and light. Because one of the big things that anytime I mention I'm a physicist to someone is I get the question, well, what is light? Is it a wave? Is it a particle? And the big thing you have to do to begin with is define, well, what is a wave and what is a particle? So that's what I'm going to be doing for you in this first podcast. And in the following podcast, I'll be explaining the different experiments that kind of set the tone for, what is light. And it will eventually accumulate, if I can learn to speak today, into kind of like some of the theories that have been bouncing off of that ever since. So to begin, what is a wave? Everybody loves going to the beach and you see, oh, the waves are coming in. Let's go run, splash, have fun. Cool. Obviously, that gives us all the big picture of a wave is, something moving that kind of goes up and down like that. Yes and no. Well, with light, you don't necessarily see so much, that natural wave that you see when you're on the beach. Instead, it's actually a propagation of fields. And I'm sure everybody's looking at me either like, oh, what is that? Or that makes complete sense. Cough, cough. Well, basically, the two fields that are used in light, or well, that create light, is an electronic field and a magnetic field. And essentially, you get an electronic field from anything that has a charge. Electrons and protons are kind of the two big ones that we talk about. They're kind of like the main particles that we really discuss when discussing charges. For this example, we'll just say you have an electron just kind of floating there. It's sitting there, it has that negative charge, and it has an electronic field around it, which will you'll feel a different level of the charge depending on how far away you are. And if you start moving that electron along any sort of distance, so just say you just start moving it straight ahead, just keep things as simple as possible, it'll create what's called a moving electronic field because that electronic field is no longer focused along a central, not moving particle. It's going with the particles, so it's kind of moving towards you. Oh, had a cool little moving towards you effect. And so what happens is if you have a moving electronic field, you create a magnetic field. And if you get that magnetic field also moving as well, which is something a little more complex than what we'll be able to cover in this podcast, that moving magnetic field then creates if you know proper grammar, a moving electronic field. So if you get that, you're building up that propagation of you have an electronic field which is moving, which creates a moving magnetic field, which creates a moving electronic field, which creates a moving magnetic field. So that's how you get that forward propagation, and it just keeps building off each other to create the wonderful stuff that we know of as light that wakes us up every morning, and we really just try to ignore. Close the blinds, go back to sleep, pretend the alarm never went off. And so when you have that moving forward, you get a measurable amplitude. The amplitude is literally just the size of the wave. It's pretty simple, straightforward. When you graph out the amplitude of something, you'll have on your y-axis, using my hand here, this will be your size of the amplitude, if I can keep straight with the camera. And then on your x-axis, you'll have time moving forward. So your wave is always going to be moving forward in time. And when you measure it out, it's kind of like you will have negative values, which is essentially the same as taking a balloon, turning it inside out, and then turning it right side in again. So as time moves forward, you're taking that balloon or moving that field forward, and when you reach your peak positive amplitude, that's when the balloon is completely right side out, and you come back down to the neutral, that's when it's about halfway. And then when we reach that peak negative amplitude, that's when it's completely inside out, and then it comes back up and reaches that neutral again, and then just keeps going forward and forward and forward. So that amplitude is directly related to the wavelength of the wave, which is how far it is between two peaks. So you'll have your first peak here, and then your second peak will be here. With visible light, we're talking about a few hundred nanometers, so a measure that you will never be able to discern with the naked eye, but clearly we can still see visible light because we do have that natural interaction with it, which is again something that's a little more complex than what we'll be able to cover in this podcast. Next, we want to talk about the definition of a particle. It's a little more simple than a wave. It's essentially any object with a measurable quantity, or several measurable quantities, actually. If you look up physical property, literally just type that into Wikipedia, you get a massive list of all the different properties they try to look at. The big ones that everyone learns from the first science class is mass and volume, and then density. And then you also have things like area, brightness, strength, durability. Cheating and looking at the list. If you have a measurable spin on the object, temperature, which goes along with specific heats and average energies. It's really a really extensive list that would take too long to cover the whole thing and to explain everything in detail. Those are really kind of the two main differences between waves and particles. Particles also have to have it's called a localized, it's a localized object, which means that, I see it here. We'll pretend my phone's an electron. The object's right here, whereas light is kind of everywhere. And when you get into some of the higher level physics, you'll see that with electrons, which is kind of a bad example, actually, you never know if it's actually right here because of the Heisenberg uncertainty principle. But again, that's something a little more complex. So with the next podcast, we'll go ahead and talk about the two major experiments that really kind of set up what's called wave-particle duality, which sounds a little complex, but you just break it down simply. Duality, two things at the same time. Waves, particles. Light is both a wave and a particle. And there's also a lot going on with that with electrons as well. But for the purpose of the podcast, we're just going to focus on light. So with our next podcast, we're going to talk about what's called constant scattering and light diffraction. See you then.